Okay, welcome back students. So this is our second module. Last class we were discussing about magnetic flux density, Lorentz force, cyclotron motion, cyclotron frequency, and we have seen the definitions of all these terms and some equations on Lorentz force and cyclotron frequency and cyclotron period. And we have found that whenever a charged particle is moving in a magnetic field in a perpendicular direction, the particle will execute a circular motion. And today what we are seeing is another situation. The earlier situation was like this. Particle was moving along the x direction and magnetic field was into the plane of this field, okay, as shown in the diagram. So we have found that force will be acting along this direction, along the y direction, and resultantly the particle will execute a circular motion like this, okay. So but in the new situation, your magnetic field is along the x direction b, and you have a charged particle v which is moving along the direction shown in the figure. So here v is making a direction theta with b, okay. So suppose that the angle between velocity vector and b is theta. Then you get another situation. In this situation you can see that this velocity vector has two components. One is along the parallel direction, along the direction of magnetic field, that we can call v cos theta, and another component for velocity v, that is v sin theta, okay. So v cos theta will be parallel to b and v sin theta will be perpendicular to b, okay. So what happens due to this situation, since v cos theta is parallel to b, there is no effect on the charged particle. That means due to the v cos theta component, particle is not experiencing any force, because we know b cross b is equal to vb sin 0. So sin 0 is 0. So v cos theta b will make no effect, whereas v sin theta, that is perpendicular to b, so v sin theta cross b. Understand? So here the angle is 90 degree. V sin theta make 90 degree with b. So v sin theta cross b will be a non-zero value. So as a result, what happens? The charged particle will have two kinds of motion. One is a horizontal motion due to v cos theta, and one is a circular motion. The circular motion is induced with the component v sin theta. So we can say that whenever a charged particle is moving in a magnetic field at an inclined angle, not perpendicular direction, an inclined angle, the particle's motion will be of two kinds. One is a straight line motion, one is a circular motion. So as a result, whenever a charged particle is moving inside a magnetic field with an angle theta to the direction of the magnetic field, then motion of the charged particle will be helical. That means a linear motion plus a circular motion. So as a result, particle starts to moving in a helical path, okay. So that helical path we can schematically show like this. So the reason is that we have a circular motion due to the perpendicular component of velocity, and we have a linear motion due to the parallel component of velocity. So, and parallel component of velocity is not influenced by the v, so there is no Lorentz force, whereas perpendicular component of v, that is v sin theta, is influenced by the v. So particle tends to move in a circular path. So the combined effect will be a helical motion of the charged particle. So we call this motion helical motion, like a spring, okay. So this is another situation of a charged particle moving in a magnetic field, making an angle other than 90 degree, okay. So there are many live situations like this even in Earth's magnetic field. Often particles from the free space, outer space are coming and they are falling at an inclined angle. So usually charged particles on the Earth's surface move in helical path mostly. So that situation is more clearly shown here. So as I have already told you, velocity has two components. One is parallel component, parallel to v, horizontal direction. So the force due to that will be q v parallel dot v sin 0, because parallel component has no angle and there will be 0. So we get the Lorentz force due to the parallel component of v is equal to 0, and due to the perpendicular component of v, we get q v perpendicular cross v. So since v perpendicular and v is having 90 degree, sin 90 is 1, so we get v perpendicular. Okay, so this way one is zero force, other is a non-zero force. Due to non-zero force, the particle moves in a certain path. And another important situation coming is when particle is moving in a helical path like this. As I told you, there is a linear displacement and there is a circular displacement. So here we introduce a new term that is called pitch of helical motion. Pitch of helical motion is nothing but the linear distance, horizontal distance traveled by the charged particle when it completes one revolution. In other words, it is the displacement of the charged particle by the time particle makes a complete revolution. Okay. So there is a revolution, at the same time there is a displacement. So that displacement is called a pitch of motion. That displacement is called pitch of motion. Okay. So that pitch of motion is nothing but the distance traveled by the particle by the time it completes one revolution. Suppose it is t, time period t, then within the time period t, how much it travels along the x direction, that is called pitch. So it is given here, it is a linear distance travelled by the particle moving in a magnetic field in a time it completes one complete revolution. So we have a derivation for it. So as we have already told you, this is nothing but a displacement of the pitch of motion, distance. So we can write the distance is equal to velocity into time. Velocity into time. Distance is equal to velocity into time. So this is a distance as a pitch of motion is a distance. So that is equal to what is the velocity along the x direction? It is v parallel. So we have v parallel here into time t. T is the time. What is that time? Time taken to complete one rotation. So even though you can note down from here, when it completes one rotation, the particle is not reaching back the original course. Instead, particle is getting displaced by a small distance along the x direction. Okay, even though it is completing a revolution but not reaching the same place. So that time is called time delay. So we have a distance is equal to velocity into time. Velocity is what? Velocity along the parallel direction. So we call it v parallel. And v parallel we know that is equal to v cos theta, as we have already shown. Okay, component of velocity parallel to the magnetic field in the period of revolution. In the previous class we have derived the equation for period of revolution, that was 2 pi m by qv. So we are introducing here 2 pi m by qv. So as a result we can rearrange the thing. So we get it 2 pi m, v is brought first in cos theta, then divided with it. So we got a new equation. This equation is used to compute or calculate the pitch of motion, or the distance travelled by the particle by the time it completes one rotation. And the pitch is schematically shown. This distance is called pitch. Okay, distance. If you take two loops, so the distance between two successive loops we can call as pitch. It's a simple way to define pitch. Distance between two successive or nearby adjacent loops. Okay, that it can be here, this can be here, this can be here, or any place, but equidistant place. So that distance is conceptually called as pitch. So now we have a problem here based on the pitch concept. a beam of protons with a velocity 4 into 10 raised to 5 meter per second enters a magnetic field, uniform magnetic field of 0.3 Tesla or 0.3 Weber per meter square at an angle of 60 degree to the magnetic field. If the radius of the helical path taken by the proton beam is 1.2 into 10 raised to minus x meter, okay, so find the value of x. That is a question, very interesting question. So here basically our purpose is to find the radius, okay, and we have already shown that whenever a particle is moving a circular path, where mv square by r will be there, that will be equal to qvb. Here we can note that this velocity is the velocity perpendicular to magnetic field, perpendicular to magnetic field. So how we will calculate v here? We have the actual velocity in a random direction. So take the sine of this, okay, v sine theta, this 4 into 10 raised to 5 into sine theta. So that will be the velocity. So you can write v is equal to 4 into 10 raised to 5 multiplied by sine 60. Sine 60. So the v is equal to 4 into 10 raised to 5 into sine 60. That will be velocity. And mass of the proton you can get from the data table or from any other source books. And b is given here, that is equal to 0.3 Tesla. And so mass, m is the mass of the proton and q is the charge of the proton. So you just rearrange it, you will get the value of the radius. That is the radius of the path traced by the proton moving in the helical path. Okay. Then obviously that answer, the resulting answer that you get will give you the value of x. Okay, I have given here the value, but you have to do it as an assignment and submit it. And there is another question you have to add with it. So that is what is the pitch of the motion? So that question is not shown here, but you have to add in the assignment what is the pitch of motion. Okay, pitch of motion I have already explained you in the slide, and this is given here, that is v cos theta into 2 pi m by 2. So you have to compute both the questions separately in a paper, and you put it as assignment. Okay. So by doing this problem, you can understand the concept of helical motion and the pitch of motion. And these are some questions which also you must give answer in the assignment. Define pitch of the helical motion. What is the condition for helical motion? Condition means components of velocity, how they should be like that. And give some real life examples of helical motion of charged particles. You can do many web search and you will get many interesting phenomena. One interesting phenomenon is aurora. Okay, aurora borealis. I will put a slide of a picture of this in your Google Classroom. You can note down it and search such a phenomena from the internet. And next class we will be talking about another important phenomenon, where also there will be magnetic field and there will be electric field, and how the charge particle will move. Okay, so here presence of both electric field and magnetic field will be there. So resultantly how the charge particle will move is a very interesting phenomenon which has numerous applications in different fields. Okay. So next class we will do that. Till then, goodbye.